Thank you for the hot discussion. I appreciate your hot discussion as an organizer, one of the organizers. Okay, this is the title of my presentation, and this is the content of my today's talk. Several years ago, I had a chance to hear the lecture by K.K. Fun and Jianya Chin about the Music X. I was inspired and interested in the concept of Music X. That is the motivation of this research. I do not need to repeat what music X is and how important the spatial variability is. Because KK and other speakers gave very good presentations. So let me go to the item 2 directly. In our approach, we use GPR. Basically, it's same as, core part is the same as grading, I think. But we use a multiple random field. That is a new point or a unique point, I think. GPR is often used for the estimation of the random component. But not only the random component, but also the trend component is estimated by GPR. So kernel or covariance instead of many basis functions. For this purpose, we use superposition of multiple random fields. With analytical solution, analytical solution makes the theory simple and it is easy to interpret the result, right? And basically the computation cost is low. Okay, let me have a very simple example, very simple example. We have 5 observation data and the horizontal axis indicates the location. So this is a one-dimensional problems. A vertical axis indicates something like soil properties. When we use linear regressions like this one, we have intercept and slope as unknown parameters, right? By least square method, we can estimate them, and then we can get this line. Let's consider the prior, Gaussian prior with this x, slope and intercept, covariance matrix, and we assume mean value, 0 mean, but not necessarily 0. We can assume any mean values. Anyway, in that case, the mean value of the estimated parameter can be calculated by these equations and its covariance matrix. We can predict the value at any locations by using estimated slope and intercept. Simply, we substitute this estimated value into this one. We can get this prediction, and covariance matrix of prediction. This theory is known as Bayesian linear regression. It's a very famous one, very famous. And from this covariance matrix, we can estimate the 95% confidence interval like this. Okay, here we use the matrix K. K takes the same form, H, covariance H. Here, H, covariance matrix, prior covariance, and H, prior covariance H. This matrix K played important role. Okay, let's increase the term, second polynomial. Then we can get the curve like this one. Let's increase more, third polynomial, like this one. In this case, each column of H matrix shows basis functions. So we use 4 basis functions, right? But in this case, we use a polynomial basis function, but there are many types of basis functions as Professor Chin introduced. A wavelet basis or a Fourier cosine basis or a step function basis, and so on. Then how many and how to choose the basis functions? To answer these questions, Professor Chin used sparse Bayesian learning, right? I think that is a very good method. And Yuan's method is close to this approach. I'm not sure, but it looks very effective, I think. There are several papers in geotechnical engineering by Professor Chin and Yuan and other persons. But this study explored possibilities in another direction. Okay, again, this is the equation for the estimation, and this is the equation for the covariance matrix. And K plays a very important role. K is called covariance of a kernel matrix, right? And each column indicates basis function. So when the large number of basis function is used, then we need a large H matrix, right? N is the number of basis functions. However, however, the number of basis function N disappear in K, right? N disappear. So if the K is defined directly, the basis function is not necessarily explicitly. So K without H, namely basis functions. Many covariance functions such as Gaussian, Markovian, Wittmann proposed. So for every positive definite covariance functions, there exists possibly infinite expansion in terms of basis function. For example, Gaussian covariance function can be obtained from the linear combination of an infinite number of Gaussian-shaped basis functions. This sentence, I took this sentence from the textbook by Rasmussen and Williams. Again, this is the equation for the estimation of the mean value and the covariance matrix. If the K covariance matrix is evaluated directly from the Gaussian covariance, it is equivalent to the regression with infinite number of basis functions. This table shows many types of covariance matrix. This table shown in Rasmussen and Williams textbook. And also this table shows many types of covariance matrix. This table is shown in this paper. K.K. Fun and Jian Chin is one of the authors of these papers. So let's extend the theory of GPR to multiple random field. Just superpose the several components like this one. In this case, n random field. And this is the equation for the n random field and its covariance matrix and likelihood function. Okay, before I apply this method to the 3D benchmark example, let me show you the application to the 1D example. This 1D example used in this paper. Also, this is a paper by Professor Chin and Professor Fun. There are three examples. First one is a linear trend component, third polynomial trend component, and cosine trend component. Around the trend component, random components are generated by using Markovian covariance. And this is the hypothetical data, so we know the true value. Standard deviation is 20 and SOF is 0.1. For the random component, let's use the true number first. Later, we estimate them later. But first, let's use the true value of standard deviation and scale of fluctuation for random component. And let's estimate the trend parameters of trend component. We tried three types of covariance functions: Gaussian, Markovian, and binary noise. Okay, this is the result. Okay, this is a contour map of negative log likelihood. So SOF versus standard deviation of trend component. This is a negative log likelihood, so minimum point means maximum likelihood estimator, its values here. With using these values, we estimate trend component. This red line indicates the estimated trend line, and 95% confidence interval. This is the case for the, this is the estimated trend, for example, 2 and 3. It looks good, right? This is the result found with the Gaussian covariance for the estimation of trend component. This is the result when we use Markovian covariance for the estimation of trend component. Estimated trend is not smooth anymore. It's fluctuating. It's fluctuating, right? And contour map of negative log likelihood. We can see a strong correlation between two parameters, right? Strong correlation. This is a result when we use noise covariance, binary noise covariance. Also estimated trend has a small fluctuation like this one. And the shape of contour map is very complicated like this one. There are even local minimum, several local minimum, right? So Gaussian covariance matrix looks good, right? Looks good. But let's select in terms of information criteria, AIC or BIC. Information criteria is often used for the model selection. So let's use it for the model selection of covariance functions. Example 1, 2, 3, and GMB. GMB is a Gaussian Markovian binary noise, and AIC and BIC. So in all examples, Gaussian case takes smallest value among these three, right? Among these three. So in terms of information criteria, Gaussian covariance function is selected for the estimation of trend component. Okay, as I said, there are 4 parameters. First, so far, I use true value for the trend component. Random component. Let's estimate the parameter of the random component at the same time. So there are 4 parameters to be identified: standard deviation and scale of fluctuation for trend and random. I prepared 100 random realizations. This dotted black line indicates the 100 random realization. And we wanted to estimate these 4 parameters by maximum likelihood method. So this is a 4-dimensional optimization problems. So I used BFGS method for the optimization. This is the result. So there are 4 parameters to be identified: standard deviation and scale of fluctuation of trend component. They are histogram, and standard deviation and SOF of random component, and they are scatter plot. So there are 100 set of estimated parameters. So I estimate the mean value of them. Trend component, standard deviation and SOF, random component, ST and SOF, scale of fluctuation. For the trend component, there is no true value. But for the random component, we know the true value. That is the 20 and 0.1. Not so bad, isn't it? And these red lines are estimated trend component. This is the result of example 1, example 2, third polynomial case. Same way, we estimated 4 parameters like this, and we estimate the trend component like this. In same way, we estimate example 3. So in this case, cosine curve trend. And this is the estimated trend curve. Not so bad, isn't it? So let's apply this method to, to benchmarking examples. Actually, all I did for this benchmarking test is just ask or order one of my students to do it. And my student, Tomizawa, did very good work. Let me introduce his result. Okay, let me skip this part already. KK explained about it. So let's start from here. There are 4 types of models. So G1 model. In this case, G1, T1. So there are only 3 Bolling data, 3 training set, 3 Bolling data. These are used observation data. And we have validation set and 12 validation site. And this is estimated one is this blue line. And red line indicate the true one. And its RMSE from number 18 to 381. And this is the largest RMSE and the smallest RSE. So this is the largest one, so worst case. And this is the best case. And computation time is around 1 minute. And for the estimation for each volume, it's very quick. It's very quick. This is the training set number 1. This is the training set number 2. So there are 6 Bolling data. 6 Bolling data. So estimation is much better, improved. And this is the RMSE and T3. Okay, G2. In this case, inclined layer with the constant property trend. And same way, this is the training set number 1. So only there are only 3 Bolling site, observation site, and estimated result, T2 and T3. So Takayuki gave us, sent his result in advance. So let's compare it. Yeah, already Professor Chin did like this. So let's compare like this. So the average RMSE, this is the result by G-Lasso. And this is our result. About average, our case is better, but best case, for the best case, G-Lasso is better. Worst case, our case is better, like this. Okay. And G3 and G4, we did in same way. But today I don't have enough time to discuss about this result, and I didn't consider this result yet. We need more time to interpret this result. Anyway, we did. We showed, let me show the result like this. So one more mission, that is the soil stratification part. And let me skip, and this is the result. IC and SBT identification ratio are shown in the top of the each figures. And RMSE and IR are plotted here for each Bolling validation set, like this one. Training set number 1, training set number 2, number 3, like this. Same way, G2 model, training set number 1 and training set number 2, 3. Let me skip the detail. Actually, I did one more case, but let me skip. And this is a comparison with the G-Lasso's result by G-Lasso. So like this. I didn't interpret the difference between them, but anyway, we could get these results. I hope we have more chance to discuss about these results after the forum or in another workshop or something like that. And we did the estimation in the same way for the G3 model, G3 model, and G4 model. Okay, concluding the remarks. We use a Gaussian process regression with multiple random field. I hope it is one of the powerful tools for the modeling for the spatial variability, not only for the geotechnical spatial variability, but it can be applicable for the wide range of spatial variability problems. Recently, we published these papers on this theory. So if you are interested in this approach, please check this paper. And other future topics, we are working on these items, indirect data. In this case, the different parameter, which has a strong correlation with the parameter in interest, we wanted to use such indirect data. Then, estimation will be improved more. And GPR is not good at sharp change like the benchmarking test, but maybe I can improve more. And reduction of the computation cost by introducing the Kronecker product for non-lattice data. Basically, the GPR computation cost of the GPR is not so high, but if we can use Kronecker product for the non-lattice data, we can reduce the computation cost more. Thank you very much for your kind attention.